Hi, my name is Sam, and this is my recording for the planetary analysis code. So to start out, what is the distance between Earth and Mars on day 732? So I've already got this put in here. This uses the distance function. As you can see, it's 6.5 million miles, which is to be expected because this is about 2 Earth years and about 1 Mars year close. So they're going to be as close, very close to the closest point in their orbits. Briefly, how did my position and distance functions work? What trigonometry functions did I need to use? So the position function uses cosine and sine to calculate essentially the x and y values, which, because the sun is 0, 0 in this grid, will be equal to the legs of our right triangle. And then for distance, I calculated the hypotenuse, essentially, which is the distance from the sun, using the Pythagorean theorem. Briefly explain how I generated the 1,000-day time series and their averages. Is there any periodic pattern visible? In the noisy cases, does the average ranking change when S increases? Try to provide a reason for this observation. So, to see the pattern, I'll run our main function and let that run for a second. So to find these, I essentially just loop through every day in the 1,000-day series and record the distances in this records dictionary. For the noisy ones, I used a normal distribution with standard deviation equal to the noise. It weakens the data a bit, but if the noise gets too high, then it essentially overpowers what the actual position of the planet is, and it becomes useless. But in cases where it's not too high, you can still see the pattern. So it's finished running. Here's our non-noisy one. As we can clearly see, there's a very clear pattern. The planets get closer and further away as they orbit at different wavelengths, I guess, different intervals based on their year. And here's the averages printed on here. And then here's the noisy one. The pattern is still visible as Mars is the largest, and Mercury you can kind of see as the much shorter oscillations. How did I form the 8x8 matrix and fill it out with the averages of the 1,000-year simulation? So it's down here. So for the 1,000-year simulation, turn it into days, so about 300,000 days, and then loop through it again, computing essentially the distance, and then finding the average distance total, and then the closest planet to Earth in that, and then turn it all into a matrix. So as we can see, those diagonal zeros going through our matrix, and then all the other ones are filled out with the average distance over the time period. The closest planet to Earth over the average time, or closest planet to Earth on average over the 1,000 years is Mercury at 9.6 million miles, which is to be expected. Thank you.